Hello and welcome to our lesson on rational functions with what we call removable discontinuities. Okay, that's a term I'm going to define for you in just a second, but first I want you to look at the very first function that I have on our paper here, the number 1 that says y equals x squared plus 3x plus 2 over x plus 1. If we were to graph this, we're going to get a picture that we probably wouldn't expect for this rational function. So let me make a fraction here. X squared plus 3x plus 2 in the numerator, and then x plus 1 in our denominator. Well, I can try to zoom in or out as much as I want. What we're seeing here doesn't look like our typical rational function. What does the graph look like to you? Well, to me it looks like a linear function. So what's going on with this graph? What's going on with this function? Because clearly looking at the equation on the paper, it's a rational function. It's got a fraction of polynomials. Well, is there something else that you notice about the function? For example, look at the numerator. Aren't there factors of 2 that make 3? Yeah. So if that numerator factors, if we factored this numerator into the x plus 2, and x plus 1, right? Because the factors of 2 that make 3 are 2 and 1. If we factor that numerator, and in the denominator we have a common factor, then that factor is going to reduce out. And the result of not only simplifying the function is also simplifying the graph. If I was to graph just the leftover piece here, what's left over is y equals x plus 2. If I were to graph y equals x plus 2, it is the exact same line. Okay? So what's happening here? Let me clear this out. We're going to get this here again in just a second. Okay? Sometimes the numerator and or the denominator of our rational function are factorable. Now this won't always lead to us reducing, but if there are factors in common to our numerator and denominator, then those can be reduced out. And when a common factor reduces out, not only is the function simplified, but in this case the graph is simplified as well. And that factor that reduces out creates or yields what we call a removable discontinuity. Okay, so think about what happens in a typical rational function. So let me go back here for a second. Let's just say I change this to a 3 so that nothing's removed. Okay, actually let's make this a little simpler. Let's say we have a parent function, our parent 1 over x, and let's shift it over and let's say up. Okay, so here's our function. What we have are technically we have places where this graph is discontinuous. A continuous graph, you're going to be able to follow left to right forever without ever having to jump from, like in this case, one branch to another branch. You're going to have one continuous graph. But if I tried to follow this one, I'm on one branch and then I would have to make a jump to get to the other one. So this graph is discontinuous. And the discontinuity happens because of the vertical asymptote in the graph at x equals -1 in this case. That's a discontinuity in our graph. It's what makes us have to jump over and go to another branch. Now, in these functions that simplify, we get rid of a discontinuity and we create a linear graph that is continuous. Okay? So if a binomial factor that includes a variable, so like if a set of x plus 1s reduce out, then there's going to be, instead of a vertical asymptote in the graph, there's going to be a hole in the graph. So let me go back again, put in this other one that we had. Was this guy. Okay, so this is the one, right? We graphed number 1. I'm showing it to you in Desmos right now. Instead of this function, instead of having a vertical asymptote at x equals -1, if I follow the function, so I'm going to get my cursor to be on this graph here, and if I try to move that around, if I go to an x value of -1, don't know if I can actually, I just can't see what I'm doing. You could probably see it, but yeah, there you go. If I go to an x value of -1, you see how it says the function is undefined there? Technically, that restriction still has to be accounted for. We just don't see it. What's happening in the graph, instead of the vertical asymptote at -1, is a hole. And so at -1, at x equals -1, and technically it's going to be y equals +1. And I'll show you how to get these coordinates in just a second. What we have in this graph is a hole. There's a discontinuous point there, but it's not the same kind of discontinuity that the vertical asymptote creates. Okay, so if the binomial factor again reduces out, if that binomial factor reduces out, there's going to be a hole in the graph that we call a removable discontinuity. This hole replaces what would have been a vertical asymptote. And we're going to have to be able to calculate and identify the coordinates for this hole, because it's something that we're going to want to show in our graphs. So the x value for the coordinates of the hole is going to be the restricted x value that got reduced out. Okay, so the restricted value here is x equals -1, right? It gets reduced out, but it's still a restriction. It's just, instead of causing a vertical asymptote, it's going to cause a hole in the graph. So the hole is going to be an open point on the graph. It's going to have an x value of -1. So instead of a vertical asymptote, we have a hole, but the x value is going to be the same there. Okay, instead of x equals -1 being a vertical asymptote, x equals -1 is the x coordinate for a hole in the graph. Now, on the top of the fraction, remember we said this factored into x plus 2, x plus 1, right? And what happened is the x plus 1's canceled out. So if I want to know the point that belongs on this graph, if I know the x value of -1, I just have to plug that x value in. So I put the -1 in here. -1 plus 2 gives me a +1. That's going to give me the y value for the coordinates of that hole. So let me just get rid of this mess I'm making again. We're going to go back and do that one more time. I just wanted to try to explain the steps as I'm going through them. So the x value is the original restriction that gets reduced out. And to find the y value, we want to take that x value and plug it into our simplified function. Okay, so for example, again here, let's just say we want to find the coordinates of the hole. We want to factor this guy out. So x plus 2, x plus 1 on the top, and x plus 1 on the bottom means those x plus 1's cancel out. So our simplified function is just a line. It's y equals x plus 2. That's a linear function, and that's why we see a line on the graph when we put that into Desmos. But there's going to be a hole in this graph. There's going to be a hole at the x value is the original restriction that got canceled out. So the original restriction right here, the restricted value, would have been a -1, but it got reduced out of the function. Now I can't just pretend that it was never there. Again, it just doesn't make a vertical asymptote anymore. It's going to make a hole. So the x value in the hole, the x value for the coordinates of the hole will be -1. And then how do we find the y value? Well, we got to take the -1 and plug it into our simplified function. So if I take -1 and plug it in here, then I have -1 going in plus 2, which makes, what I have is y equal to a -1 plus 2, which makes a +1. So I have a y value of +1, and those would be the coordinates for the hole. Okay? And just so you can see it again one more time, I would put my function in. I see a line there. Now if I put in the coordinates for the hole, the -1, 1, I can use the settings here to make that an open point. Okay, and I can even click a label here to show that's the hole in the graph, and now I have exactly what I would like to see when you do this in your practice. Okay, so you're going to graph the function and identify the coordinates of the hole and make sure you show the hole as an open point. Okay, and we'll do more of those in a few minutes. But this is another one that's going to have a hole instead of an asymptote because this thing reduces. This time the bottom of the fraction is factorable. What are the factors of 10 that make 7? Well, they're going to be +5 and +2, so it's going to factor into an x plus 5, x plus 2. And so those binomial factors reduce. So our simplified function is 1 over x plus 2. So our graph, instead of having two vertical asymptotes, instead of having a vertical asymptote at -5 and then a second one at -2, it's only going to have one vertical asymptote, right? -2 is still going to be in there as a discontinuity, right? But now, instead of two vertical asymptotes, we have a vertical asymptote and a hole in the graph. So let's find the coordinates of the hole. The hole is going to be at, the x value is the restriction that got canceled. So the restricted value that got canceled out was a -5. So -5 is the x value in the coordinates of the hole. And then to find the y value, it's a point on the new graph. So I need to plug my x value into the simplified function. So y is going to equal 1 over a -5 plus 2. So that's 1 over -3, or a -1/3. So -1/3 is the y value in the coordinates for that hole. Okay? So we know how to simplify the function. We know how to find the coordinates of the hole. So now we're going to practice doing the whole thing. Okay? We're going to practice finding the coordinates of the hole and creating the graph and putting it all in Desmos to verify our work. So if I want to graph a rational function that simplifies, I'm going to factor and reduce, factor and reduce, and then what I want to graph is the simplified function. What's left over? So I'm going to graph the simplified function. Now it's possible, as we see in examples 1 and 2, it's possible that our simplified function is linear, so we're graphing a line, but it's also possible that our simplified function is still rational, so I might still have a graph that contains an asymptote and branches. Alright, so we have to look at what's left over and graph what we have left over. Just make sure that we are accounting for the original restriction that got reduced out. So we want to find the coordinates for the hole and make sure that we include that in our simplified graph. And then we're going to put everything in Desmos just to confirm, and also because that's what you're going to be submitting in your practice assignments. Okay, so you can use Desmos to verify your work and then upload screenshots to Canvas for your practice. Okay, so let's look at this function here. The top is going to be factorable, so this time I'm going to go through the whole bottoms up process here. 2 times 15 is 30. I need some factors that are going to make a -11. So what could I use? Well, 6 and 5, if they're both negative, will multiply to a +30 and add to add to -11. So these are both going to be divided by 2. That means the top of the fraction, this one's going to reduce to 3 over 1. The top of the fraction is going to factor into 1x minus 3 and then 2x minus 5. And let me just scoot this over. And the bottom of the fraction still contains that x minus 3, which means that x minus 3 is now going to reduce out. So we're going to have a simplified function. Our simplified function is just y equals 2x minus 5. So let's go ahead and graph this simplified function. Remember how to graph a line? We can use our slope and our y-intercept. Now, obviously, we have Desmos that can do this for us too, but you should be able to graph a line. So we have a y-intercept at -5, which means I did not create a good graph here. Gosh, guys. And a y-intercept at -5 means it's going to cross the y-axis down here somewhere at -5. And then from there, we would rise, because the slope is 2, or 2 over 1, we would rise 2 and run 1 to get to the next point. So technically, I should be starting down here, and then I could go up 2, right 1, make another point, and then I would connect those points to make my graph, okay? But I did not put a good graph on my note sheet here, so I need to find a couple of other points here. So this is another route you could take to graph. So if I only need 2 points to graph a line. Let's say I plug, not a 0, I already established that's going to be 2. Let's say I plug, let's say +2 in, okay? If I put a 2 in here, 2 times 2 would be 4, 4 minus 5 would be -1. So at 2, -1, I'm going to have a point. And then let's say I put, I don't know, 5 in. If I put 5 in, then 2 times 5 would be 10. 10 minus 5 would be 5. So at 5, 5, I've got another point here. And technically, this is what my line should look like. Okay? So that's what my line should look like. However, there should be a hole in the graph here. And actually, this was 2, -1, and then 5, 5. Before I connect these, where am I going to put the hole in the graph just so I can make one fluid line after I make the hole? Where am I going to put the hole in this graph? Well, let's find our coordinates. So we're going to have a hole at, what's the original restriction that got reduced out? So right here, instead of having a vertical asymptote at 3, we had a restricted value of 3 that got reduced out. So that restricted value is still restricted, it's just going to be in the form of a hole instead of a vertical asymptote. So 3 is the x value in the coordinate for the hole, and then to find the y value that goes with that, I'm going to plug that x value in to my simplified function. So y is going to equal 2 times 3, which is 6, minus 5, which is 1. So the coordinate for the hole is going to be at 3, 1. So at 3, 1, 3, 1, I'm going to make a hole in this graph. Okay, so now from here, I just want to make this look proper. There you go. That's what your picture should look like. Okay, if you were doing this on paper, now I understand you aren't doing a lot of work on paper, so what will this look like in Desmos? Let's put all this in Desmos. This is what you would be submitting. So y equals, let's type the original function in, 2x squared minus 11x plus 15. Oh, I forgot to hit the fraction bar first. That's okay. If I use a parenthesis to close that off and then hit the divide, I can not have to erase everything. Let's see. Y equals, okay, so the bottom of the fraction has an x minus 3. And there's the same picture I have in my paper. I just need to show the hole. Now, again, if I tap on the graph here and just follow the graph with, if you use your finger or your mouse if you're on the computer and follow the graph, you can see when you get to, where am I at? You can see when you get to positive 3 that it's undefined, right? We want to show that. We want to make sure that stays there. So I'm going to type in the coordinates for the hole. 3, 1, and that looks correct on the graph there, and I want to label it, but I want to show it as a hole. So I'm going to press the settings button, change this to an open circle, and I want to make it blue just so that it matches, and a screenshot of that entire thing, the graph, the function, the hole, all of it is what I want to see in your submission for your practice. Okay? Alright, so let's try this again. Let's see. Here's another one. Hopefully I put a better graph on my note paper here. Again, this is going to simplify because the bottom is factorable. So on the bottom, factors of -24 that make, save myself some space, factors of -24 that make -2 would be -6 and 4. So the bottom is going to factor into an x minus 6 and an x plus 4, which means the x plus 4s are going to cancel. So what do I have left? Well, technically a 1 on the top of the fraction and an x minus 6 on the bottom. Okay, so my simplified function is still going to have an asymptote. Instead of having one at 6 and -4, it's just going to have a vertical asymptote at 6. So this function has a vertical asymptote at x equals 6, right? Because 6 minus 6 would still make a 0 on the bottom of the fraction. So at positive 6, I'm going to make this a vertical asymptote. And then what about the horizontal asymptote? Well, this is a transformation of the parent function, and I know that -6 made the whole graph go to the right 6, which is why we see that vertical asymptote shifted to positive 6. It's not shifting up or down, right? So we should still have a horizontal asymptote at 0. We could also look at the degrees. The degree of the top is 0, the degree of the bottom is 1. Since the degree of the top is less than the bottom, a horizontal asymptote is going to happen at y equals 0. So horizontal asymptote at y equals 0, just like the parent function. So let me make these with highlighter here. So positive 6 and 0. Okay, and there's no reflection on this graph, which means our branches should be in the same corners as the parent, so we should be looking something like this. Okay, so that would be the graph. if all we were graphing was y equals 1 over x minus 6. However, we have to account for the original restriction that got reduced out, right? -4 was restricted from our original function. Now, it didn't create an asymptote because it got reduced out, but it's still going to make a hole in the graph. So now we have to find the coordinates for this hole. There's going to be a hole at the x value for the hole. The x value for the hole is going to be the original restriction. So the restricted value that got reduced out here was x equals -4. That's going to be the x value in the hole. Now I'm going to plug that in to my simplified function. Oops, pen, green. Okay, plug that into my simplified function. So y is going to equal 1 over -4 minus 6, which is a 1 over -10, or a -1/10. And so at -4 and -1/10, -1, 2, 3, 4. Oh, I didn't go quite far enough with my branch here. -4 and -1/10 is going to be over here somewhere. -4, -1/10 is going to be like over here-ish in my graph, and so that's the picture I have tried to create on my paper here. Now let's get this in Desmos properly. So y should equal, let me make my fraction first this time. Let's see, x plus 4 in the numerator, x squared minus 2x minus 24 in our denominator. And this still has a vertical asymptote at x equals 6, so I want to show that. And instead of a second vertical asymptote at -4, there's a hole. So the hole we said was going to be at -4 and -1/10. And this is all looking good here. Let me just go to my settings, and I think black's okay there. Let me make this match black. Actually, let me make this match purple. Make that open. I don't care about the colors, so your colors could be all different, but let's just verify that hole looks correct when it's all zoomed in. But let me hit the home button again. This is what I want to see. Oh, I forgot one piece. This asymptote should be a dotted line. So there we have it. Okay, I have a vertical asymptote there. Let me put in the horizontal asymptote. Y equals 0. And let's make this red and dotted. And let me change this one to red too. There we go. So I have a vertical asymptote at 6, a horizontal asymptote at 0. I have a hole in the graph at -4, -1/10, and the branches. So all of that is what I want to see. I want to see all of this stuff, the function, the asymptotes, the hole, all of the equation stuff written here, as well as the picture of the graph and everything labeled, dotted, dashed lines, hole, all of that. So that is what you would submit to your practice assignment. Okay? All right. Let's try another one. Let's see. This guy is going to reduce in the numerator and denominator. So the numerator is a difference of squares. X squared minus 16 becomes x plus 4, x minus 4. And the denominator, factors of 24 that make 10 are 6 and 4. So we have an x plus 4 and an x plus 6. So my simplified function is x minus 4, x plus 6. Again, this is still going to have a vertical asymptote in it. It's still going to look like a rational function should look, with branches and an asymptote. So specifically, let's see. We're going to have a vertical asymptote at x equals -6, because -6 would cancel the +6 and make the 0 there. And then the horizontal asymptote, where's that going to be? Horizontal asymptote at, well, this time our degrees are equal. This is not a transformation of the parent function. So if I look at the degrees here, since the degrees are equal, if I divide these leading coefficients, 1 divided by 1, I get 1. That means I'm going to have a horizontal asymptote at y equals 1. So let's see, y equals 1 is going to be there, and x equals -6 is going to be there. And because, again, this isn't a transformation of my parent function, I don't know exactly where the branches are going to be. So I'm going to use Desmos to figure that out. But let me go ahead and calculate the coordinates for the hole real quick. Alright, there's going to be a hole in this graph at where? Well, the x value for the whole is going to occur at the x value that was reduced out. So here we had a restricted value of -4 again that got reduced out. So -4 is going to be the x value. And then we're going to plug that into our simplified function. We're going to plug that -4 into the simplified function to figure out the y value that goes with that x value. So y is going to equal -4 minus 4 over -4 plus 6. So -8 over 2, which is -4. So -4, we're going to have a hole in this graph. So -4 is going to be here, which tells me I'm going to have a branch on this side of the graph. And most likely the other branch is going to be in this corner. But let's just verify. And let me get rid of all this. Okay. So y equals x squared minus 16 on the top. X squared plus 10x plus 24 in the bottom. Vertical asymptote at x equals -6. Horizontal asymptote at y equals 1. Everything looks right so far, right? And then the coordinates of the hole in the graph should be -4, -4. So -4, comma, -4. And there's the hole in the graph. And let me just, again, I'm going to use my cursor to go over to -4 and make sure that was the correct. Yeah, see how it says -4 undefined, right? -4 is the correct x value. And the point that I've plotted there looks like it's in the right spot. So now I'm just going to fix some stuff here. I'm going to make my graph blue. And I'm going to make my asymptotes red and dotted. And let's make this, oops. Let's make this one red and dotted. And then let's make this an open point. And let's match it with the graph. And there it is. So that's everything that I would like to see. Again, I showed the label there. Everything I would like to see plotted in Desmos, and then screenshot that and put that into your practice. Okay? So, it's a lot, I realize. Just try to be organized with your work, and I think it'll go all right. I think if you feel confident, this would be a good place for you to pause the video and give this last one a try. On this last guy, let's see, factors in -30 that make -1 would be -6 and +5, and I'm writing my signs wrong. -6, +5. So if the top factors into x minus 6 and x plus 5, and there's an x minus 6 in the bottom, then that x minus 6 is going to cancel. So our simplified function is just going to be a line. And this time, I put an appropriate picture for me to be able to graph this line. So a slope of 1 and a y-intercept of 5 means I'm going to cross this graph. Y-axis is going to cross at 5. So b being 5, that means I have a y-intercept of 5. So on the y-axis at 5, I make a point. If the slope is 1, which is 1 over 1, then I can rise 1 and run 1 to make my next point. So I can go up 1 over 1, make as many points as I want. If I connect those, I'm going to make my line. Now before I connect, I want to go ahead and make a point for the hole in my graph. And I want this to be blue. So let's put a blue point there. And this is just to be 1. Okay, so there's going to be a hole in this graph at, where are we going to be? So the x value that got restricted out is going to give me the x value for the hole. So here I had a restricted value of x equals +6 that got reduced out. And then if I take that +6 and plug it into my function, y is going to equal 6 plus 5, which is 11. So 6, 11 should be the coordinates for the hole. So at 6 and 11, I'm going to make the hole, and then I can just connect these to make my line. Okay, so now let's confirm. Get rid of all this. Y should equal fraction of x squared minus x minus 30, and then x minus 6 in the bottom here. So my picture looks right. Let's use the cursor here and scroll up till we see X equals 6 should be undefined. Yep. Okay. Now let me just plot that point. So 6, comma 11 is where the hole should be. Now I just want to make that an open point. I want to make it match my graph, and there it is. That's all you would need to show me for your practice assignment. Okay? Hopefully that makes sense. I know it is a lot to take in. Again, just piece by piece, okay? One thing at a time. Try to follow the steps. Try to follow the notes. And as you're working through the practice, if you need some extra help, as always, I'm here for you. So just